At 1344, June the 25th, 1983, a remarkable experiment started in Oxfordshire. It was the first plasma in the shiny new JET experiment, the Joint European Torus, a fusion experiment that was supposed to last for 10 years. 40 years on, it's still going, though in a week or so, they're going to be firing its very last plasma. I'm Roland Pease, and I've been following the progress at JET since its very inception. And I've come back to the control room where that very first pulse was fired off to look back at the extraordinary things that they've achieved here, to meet the people who made them happen, and to look at what the future holds for Culham, for JET, and for fusion. And here we are, and in fact, you have joined the broadcast just as over there at the other end of the control room, they're winding up for another shot. There's going to be a big blast of heat in JET any minute now. You'll hear the noise probably in the background. I'm joined to start with this hour and a half festival of the science that's been done at JET. I'm joined by Fernando Rimini, and you are the Senior Exploitation Manager, which is a lovely phrase. What do you exploit?
We exploit the machine.
You exploit the machine, and it's about to happen. And Matteo Baruzzo, you're the task force leader. I understand that means you're in charge of, or you're involved in planning the series of experiments?
Correct.
You've been busy the past few weeks.
Yes.
Very busy?
Yes. In JET and other European tokamaks as well.
Okay, so it's the whole of Europe you're working with.
Yes.
Brilliant. And Nick Malshaw, and you're the chief engineer, so this is your baby.
Yes, so I and this lovely team of people here deliver the machine for them to play with.
And it's quite a machine. I mean, we can't see the machine itself, which is, I think, somewhere over there, isn't it? Yeah. Massive machine. You'll have seen the pictures. You will be seeing some pictures also of the machine and of its insides during this podcast. Now, which of you has been here the longest?
Oh,
Confession.
No
Fernanda, when did you join JET?
I joined in 1987. I came for a year thinking, yeah, I'll stay. Never left.
Never left. Well, as I say, the original plan was that it would be running for about another
7-8 years, something like that, from 83. So.
I mean, what an amazing machine it is. But you joined in a sense when it was really hot and new.
It was hot and it was new, and it was the time before a lot of the changes. One of the beauties of this machine is that it has one of the reasons why it lasted for 40 years is that it has gone through so many changes to keep up with the physics and with the engineering and with the sort of improvements in the engineering as well. So when I came in, the machine was nice and up-down symmetric, for example. There wasn't a diverter. And then in 92, it was all eviscerated, diverter built in, and a completely new phase of the exploitation. I
mean, Nick, I do wonder slightly whether this is a bit like the ship of Theseus, the boat that, at the end of the voyage, every timber had been replaced, yes, but it was still the ship of Theseus. How much have you replaced over there?
Yeah. Well, the core of the machine is the same, but plasma-facing components have been changed multiple times. Diagnostics are always being added and upgraded. And so, it's, yes, like the 100-year-old broom, as you say. And,
Matteo, we haven't actually talked about what a plasma is. So I think, can you just take us into some of the very basics of what's going on? In fact, probably is going on over there. I hear some buzzing going on. This is a gas you have inside
there's
this
a plasma
huge
now.
torus. Oh, it's actually firing up. I wish we could cut over to it. The plasma is...
Yes. So the plasma is basically an ionized gas that gets created through magnetic fields that we produce in the tokamak coils. And within this gas, there's a current that flows, and this
a current, come on.
a current.
What kind of a current?
It's a big one.
It's a big one, come on.
It can get to, on jet, it can get to about 4 megaamps, 4.5. Then,
4 million amps.
Yes.
Yeah, so
Yes,
that's
exactly.
not
It's
like
a
you
big
get in a
one,
light
yes,
bulb. Yeah.
yes. The resistivity of the plasma is very low, and then we can drive a big current in it. And this current creates also the fields, part of the fields that confines the particles of the plasma and keep it nice and cozy inside and warm.
And the temperature, you say again, warm, come on.
Yes, it's between 100 and 200 million degrees, and it's it's a very high heated plasma, and then we heat it from outside as well, with microwaves and beams of particles.
So this is the biggest microwave oven probably on the planet at the moment.
Probably.
And 100 million degrees or 200 million degrees, the sun, the center of the sun is 15 million degrees. So this is hotter
Yes.
than the center of the sun. And it's all for, Fernanda?
And it's all for creating power for eventually producing energy and electricity. So the whole idea is that in certain conditions, so when the plasma is hot enough, the plasma has to be big enough, so the machine has to, the volume has to be sufficient. It creates the reactions that are happening inside, create energy, and when the energy that comes out is more than what we put in, then you can use that energy to produce electricity.
Most of the time, you put in heavy hydrogen into this machine. So that's deuterium. And that sort of doesn't do very much, but you're looking at the behavior of all these atoms when they're getting so hot, how you actually manage to contain them in the magnetic bottle, is that right?
Yeah, so from the point of view of the way the plasma behaves, using hydrogen or this deuterium is almost the same, but it doesn't produce neutrons, too many neutrons, so the machine is nice and safe. It's not radioactive. We don't need to handle anything.
I think
nasty.
Nick likes it that way.
Yeah, no, we like it. We like it very much that way.
no, I like the excitement of running with tritium.
So that's when you put in the tritium fuel, and that's when you're actually getting the fusion reactions that you
Yeah.
really want.
For the last 2 years, we've run experiments with the even heavier hydrogen, tritium. So we ran about nearly a year of pure tritium plasmas, which nobody's ever been able to do in the world before. And then we had a short burst of deuterium tritium, which is the fuel that will fuel fusion in future. And then we've repeated some of that. And so we've actually become quite good at running with this precious and radioactive gas tritium. And it's become easy, hasn't it?
And when we say it's precious, and the reason why we don't do it all the time, it's also that we have a little bit on site and we recycle it continuously, so that we reuse it and we take it and reuse it and purify it.
I mean, it's
Because
pretty rare, isn't it? You have to
fairly
make
rare.
it specially,
Yeah,
and it doesn't last very long.
it doesn't last about 12 years.
12 years, but okay, so it's two tritium life cycles almost then, since the very first experiment. So I wrote about this in 1991 when you did the first tritium deuterium experiments, and there was a lot of excitement back at the time. Why do you need to keep going back to it, Matteo?
Well, it's a natural process. On the first DT campaign, we actually produced important records with lots of fusion power, but we also realized that the material of the first wall of jet would retain a big part of the fuel that we were injecting, and this, for safety reason, was not acceptable. And then,
Sorry, when you're saying retain, it was sort of sucking it up like a sponge.
yeah, exactly. The carbon acts like a sponge and then stores the fuel inside. And in order to avoid this, in the last 20 years, different fusion devices has moved towards a metal wall, and JET has done that too. And so we would need to prove that the DT experiments are compatible with this new metal wall.
And this is what you were talking about, replacing so much of JET to sort of bring it up to date.
It's partly about compatibility, but the other thing is we've developed this capability of the machine to supply much larger quantities of tritium. So the preliminary experiments, they only had a fraction of a gram of tritium, and they weren't able to recycle that, whereas we've now got some tens of grams, and we've been able to recycle it through the machine for a whole year. So in total we've put over a kilogram of tritium through the machine, because we now have the facilities to recover the exhaust gases, separate them back out into tritium, deuterium, and hydrogen, and reprocess everything so that you have a continuous cycle.
I mean, I have to say, these times people should love the idea of recycling your exhausts. And this is the other thing, you put in a diverter so that as well as the running the plasmas through this huge torus, this huge donut that you have here, you're then sort of extracting the material at the end of it all, cleaning it up, extracting the stuff like the deuterium.
Yeah, I think the biggest step change in the performance of the machine was in the early 90s when the diverter was installed, and it's very important. Well, it acts a bit like the exhaust pipe, but it's also important for impurity control, and it stops you getting so many impurities into the core of the plasma.
Because it has to be clean.
Yeah.
I mean, it's interesting, Fernando, when we journalists talk about fusion, we make it very simple. Oh, it's controlling the power of the sun. You put deuterium and tritium in there, you whack it all together, and you get electricity out. And there are so many of these details that we never actually go into because
they're very complex, and people lose patience with us when we go into way too much details. I think you were asking about what happened. One of the ways in which the fusion has really progressed is the control, the area of the control, the area of the real-time control systems that we can use. At the beginning, this machine was running on an analog systems, and now we've digitized all the data that comes in, and we run on fairly complex systems that use AI as well. So we are incorporating all these things to control the plasma better, to operate it better.
I mean, because I guess it's a massive engineering operation as well as a physics operation. So, I mean, you've gone through goodness knows how many generations of computers, presumably all the sort of electronics that are driving the magnets and those kind of things. Those have changed?
Yeah, that has changed. A lot of that, a lot of the core stuff is still the basic one, sort of the high power amplifiers. A lot of them are still very the very basic ones, but the way we control them has changed. I think, can I pick up on something that you said? You said it's an engineering and you said it's a physics, as if they were two different things. They are not.
They're not.
So my point always is that at JET, they are not. And this is why JET has been so successful, because the physicists and the engineers talk and they work together.
And the physics that's in the plasma, that's this sort of hot, I always think of it as a kind of uncontrollable piece of jelly that you're trying to squeeze with magnets and funnel with magnets and so on. That's the physics, is it, of how they react to the fields, to the currents, and to presumably also to the tritium heating it up inside. Yeah. And then the magnets are, the engineering is all the rest of the stuff doing that work. Nick?
Yes, and picking up on something Fernando said, a lot of the old power supplies that were originally used for one function have been repurposed to other functions as we've upgraded the power of some of the amplifiers. And so there's been a lot of recycling of things on JET to just keep advancing.
We have had a question from YouTube, and there's a means for anyone to send in questions, and we'll try to feed them into this discussion. Right, okay, I think this comes from an expert. When will we reach Q greater than 1?
Who do
Q
you
is a
want?
performance. Who wants to answer that?
So JET wasn't designed for Q greater than 1.
Is this the amount of heat coming out versus
The amount of
heat
heat
going
coming
in?
out versus the amount of heat going.
So we will, our record is at the moment Q 0.7, and we will probably not reach Q equal 1 on JET. So this emission will be for the future devices in fusion, like ITER, for instance.
So, for example, ITER.
ITER is definitely Q
Yeah.
equal 10, but there are other machines, other private public companies that are aiming at Q of 2, which is already quite a big step.
I mean, in a sense, this goes back to the point that there's so much physics and engineering to be done to control these plasmas. I mean, this is like fine-tuning a petrol engine without putting the petrol in. And there's an awful lot of that to be done before you can actually start making the fusion. But the lessons that you're getting from here are going to inform ITER, they're going to inform the small companies and so on that are being spun out almost from JET here.
Yes, and they will do more. I mean, the data that we collect here will be used to validate the models the physics models that we use in order to predict performance of future devices. And we've done this exercise very much into the detail for predicting the performance of DTE2 and DTE3 campaigns. And one of the great successes of this campaign is that actually we could match with the science data with the prediction that we had made with our codes. So this gives us confidence to predict this to larger devices.
Just knowing what you're doing, knowing what you think is happening, it's a triumph.
Sharpen our tools in order to be able to understand what will happen in the future.
And remember, the question of Q is not quite as simple as it seems. So there's a physics Q where you put more, you get more energy out than you put in, and there's an engineering Q where you get more energy out than all of the power that goes to the whole plant, which is obviously a different number, and that's a bigger challenge. But I think ITER is planned to get to better than a Q of 1 in an engineering terms, and better than 10 in physics terms.
Okay, one word from each of you. What, in a word, has been the biggest achievement here at JET? Fernanda.
Probably DT, doing DT, not just the records, but the physics, the wealth of physics of DT, because the conditions are different. Once you go into hydrogen deuterium DT, conditions are really, really different. So having all these campaigns over the years, I think, has been the main success.
Matteo, you've got this oversight over all of Europe. Go on.
Yes, and in addition to that, I think the latest, let's say, interaction we had with the programs happening into the other tokamaks, and the way we could extrapolate, extrapolate experiments from smaller devices to JET could give us like a stronger base in order to predict and extrapolate for fusion experiments.
And Nick, it's still going.
Well, for me, the biggest achievement is the way that people from so many countries have worked together, and they've understood things like quality assurance and quality control and what the difference is. And the end result is we've got a machine that works, and you can tell it works because you can see it working in the background.
It's fantastic.
It's measurable.
Fernanda, Matteo, Nick, thank you very much for joining us. Now, before I came here, I spoke to Tony Donnet, who was until I think today, the director from Eurofusion for this whole project. And here's the tape. Well, hi Tony, thanks for joining us. Quickly, just this is a journalist way of doing this. Introduce yourself rather than me trying to get your credentials right.
Yeah, well, I'm Tony Donnet. I'm program manager of Eurofusion and responsible for also the exploitation of JET since 2014.
And well, I wanted to start with that moment. You joined JET at a time when it was just beginning its sort of, I think, the final but most important leg of its operation. I'm quite curious. Do you remember what it was like when you took on the responsibility?
Yeah, it was it was a kind of difficult time in the sense that we were struggling in getting Jet back to the same performance as we had before with the carbon wall. So in the early 2000s, we changed the wall from carbon to beryllium and a tungsten diverter, and operating a machine with metal is much harder than a machine with carbon. And we needed to learn again how to operate a machine. There were also years where we struggled a little bit with aging of some components. Not everything ran well, so the campaigns were a little bit difficult. But ultimately, all the scientists got it going. It's really the dedication of the whole JET team which is behind it. And we got fantastic results in the recent DT campaigns. So it was worth it all.
I mean, clearly, this was an important phase because this is all part of the preparation for ITER to make sure that ITER starts with the best possible sort of knowledge it can.
Absolutely. So originally, well, let's say when ITER was designed, we only had experience with carbon machines. And still, we needed to have a demonstration in a metal wall machine, whether it can work, and also with a fuel deuterium tritium. So it was very important to do these experiments on JAD, and we have shown that we can do it. We need to operate the plasma completely different than we do in a carbon machine, but we can manage. And actually, we got the performance much better than we had in 1997 with a carbon machine. And at that time, we had a higher plasma current. So you can say that we are much better now in running the machine. And in the preparation for ITER, this is fantastic.
One of the things you said in a couple of papers on JET, which I found really striking, was that it's not just the machine that matters, but it's also the team, that actually it takes time for all the different members of the team to gel when you start running plasma operations, that it's actually requires that kind of level of integration, I guess, as well.
Yeah, in that sense, JET is unique. It's a kind of international family. So JET is right from its start in 1983, international device. It takes many years before you can operate a machine, before you're licensed really to run the high performance discharges. It's about 4 years to train a session leader. And so the people, they know each other a long time, and they're doing the discharges. Of course, you go to good times when it runs fine, go to bad times, because sometimes there's weeks where you really don't get anything sensible out of the machine. And there's this bond, which is really, it's a kind of big European family. So everyone feels connected to JET. And this is very important to have this feeling that the machine is ours, that we together try to get the best out of it.
Fusion research has, certainly since the 60s, the job of the leaders like yourself is half science, but, well, maybe give me the proportion. How much of it is politics? Because it's always been difficult politics, and you probably spend an awful lot of time in Strasbourg and Brussels, and go on, spill the beans.
It's not too bad, but yeah, indeed, there's a lot of politics, and I think the problem is really to get the funding right. And I'm convinced we can get fusion to work before 2050, provided there is sufficient funding. And my view is we need to treat fusion as a Manhattan-type project or moonshot program, where you just put researchers, industry together, where you agree with politicians very quickly on a site, and you go for it, and then you can do it.
You think there's still a place? I mean, obviously you do. You would be doing this, but this is your chance. When windmills and solar farms are working so well, you're convinced that we need something like fusion for the long-term future.
If you look at let's say the CO2 emission of the various countries in Europe, the clean countries are the nuclear ones. So that's Sweden, that's France, and of course the countries which have a lot of natural resources, like Iceland with its hydropower and thermal power, etc. Norway, kind of similar. So we really need to go to nuclear, either fission or fusion, because with renewables you don't get there completely. It's nice, it's a nice addition, but we need definitely nuclear, and fusion has a number of advantages above fission. And we need to get it work because we don't get produce that much waste, and it's safe, and it's a great way to go. And we just need to spend the money on it. I cannot understand that. Well, again, Germany is spending like 25 to 30 billion euro per year subsidy in wind and solar. For fusion to develop. So this Manhattan type project, which I mentioned, we only need 1 billion a year for the next 20 years. And we can do it, I'm convinced.
I know exactly what you've got on your background behind you, the innards of JET. By the way, do you know what I've got behind me?
Yeah, well, that looks like JET in the very initial stage that must have been 1980, roughly.
It is very good. That is. I think it's a fabulous. In a way, it's sort of, for me, I chose it because it sort of, it encapsulates, I think, the hope and the dynamism at the very beginning of this extraordinary mission.
It's amazing, well, I remember we have that picture also in the JET foyer. And I was there in 2016 with Bernard Bigot, who was that time the DG of ITER. And there were these pictures, 1980, 1981. And then I told him, Bernard, this is where you're now in ITER. So in 3 years from now, you will be here. And I showed him the ready jet. And of course, he had to laugh.
Yeah, it was the ITER construction. It really it reminded me of the intensity of it.
I must say things can go faster. I was basically last week in China. I just returned 1 hour ago from China, and I visited the site where they're building BEST. And BEST will be a device which will work with DT and will be in operation in 2027. And they showed that they just have dug out the pit. So the pit is there. They start building next week. The building should be ready within 2 years, and they're already winding the coils. They're building the machine, and I'm convinced that, well, maybe it's not 27, but then 28, China gets it going, and they treat it really like a Manhattan-type project, and we should do that also in Europe. That's the only way forward, and we can move fast, but we need to be clever and learn from the lessons we've seen from ITER, also JET. We have learned many things which go well. We have also learned things which don't go that well, which we need to do different.
Well, it really does sound like the spirit of 1980, 81, 82, 83, and the intensity. I was reading the papers about back then, about INTOR or NET, the next European Torus, all the designs. I think there was such a dynamism there, and hopefully, I don't know, when the bar, the relay is picked up by ITER. JET's place in history, in fusion history, will be absolutely central.
Oh, absolutely. JET has been for over 40 years the most central machine. So there have been 3 large machines in the past. So there was TFDR in the US, there was GT60, later it was GT60 upgrade, and now GT60 SA. Which have been all 3 very nice machines. TFDR was already closed in the mid-90s, and GT60 is now upgraded, so that will continue for another maybe 20, 30 years as a satellite to ITER. But it's really, these machines are really landmarks and have brought the whole field of fusion physics much further.
Well, Tony, thank you so much for talking to us. I believe at the same time, more or less, as they'll be turning off the power at JET, you're retiring as well. So you're looking for the next, or at least you're leaving Eurofusion.
Yeah, well, I hope that I still can now and then do some work for Eurofusion, whatever. I hope I will not be completely out. Yeah, it's interesting to note that I started my career in fusion, well, just a few years after JET came alive. and I'm stopping at the same time, actually on the same day even. So that's a coincidence. Yeah.
Hi, I'm Joelle, UKAEA Jet Science Program Leader. Today I'm in the Jet Control Room where we finished recently the DTE3 campaign. This was the final campaign making use of Jet's currently unique tritium handling capabilities. Like all Jet campaigns, this was done as part of the Eurofusion Science Program. It involved more than 300 scientists from 30 different labs from all over Europe, including UKAEA, and with several scientists from further afield. It also relied on a similar number of technical and plasma operators. So this campaign was designed to study how deuterium-tritium plasma behaves compared to deuterium to improve our predictions for ITER and fusion power plants. But also specifically, the campaign addressed 3 different challenges remaining for ITER and power plants. The first challenge has to do with minimizing the power load getting to the diverter plate. So the diverter is the part of the vessel where the charged particles escaping from the plasma are directed by the magnetic field. This can lead to very high power load, higher than what can be tolerated by present-day materials. Now, in DT3, we tested a method that is going to be used in ITER, and that's to inject neon so that the power is radiated before it gets to the diverter plate. And we demonstrated that, indeed, this way you can get a nice cool edge, cool diverter plates, while at the same time retaining a nice hot plasma for high fusion power. The second challenge we addressed is the need to control ELMs. So ELMs are spontaneous and periodic release of plasma energy and particles to the first wall. They happen when the plasma gets into H mode, which is high confinement mode with an edge barrier to heat. And this is required to get to the high fusion performance needed by power plant. There are several methods for ELM control being studied in the world or at JET. For example, using specially designed magnetic coils or injecting frozen fuel pellets. But another way to deal with this is to try to design a plasma scenario that has intrinsically small or no ELMs. And in DT3, we tested for the very first time in deuterium-tritium a scenario with small ELM that was first demonstrated on medium-sized tokamaks elsewhere in Europe, so ASDEX, Upgrade, and TCV. And that was then successfully developed in deuterium and JET and performed also very successfully in DT3. A third challenge is demonstrating high fusion power plasma in a machine with a tungsten diverter. Now, tungsten has many qualities that make it attractive for fusion power plants, but it's very tricky to use because it radiates a lot. If it gets into the plasma will just collapse. So in JET, in previous campaign, we had demonstrated a regime where we can keep the tungsten out of the plasma because of a very hot plasma edge. Now in DT3, we expanded the operational space for this regime, which provides us more data to predict how this can take place in ITER or fusion power plants. We also went back to the plasma scenario that delivered the fusion energy records in DT2. This was in itself a demonstration of the compatibility between high fusion power and the tungsten diverter. So this time we wanted to go back to study a bit more the underlying physics. And we were very pleased to see how reproducible this was. On the very first go, it just went beautifully. That was a very nice result. Now, these results and many others were all performed within 7 short but very intense and exciting weeks. One thing that the teams noted is how easier it was in DT3 compared to DT2 because of the experience we gained in DT2. So now an important aspect is to make sure we can make ITER and fusion power plant benefit from this experience, as well as from the new physics uncovered by these experiments. So today the control room looks very quiet, but we're very busy cleaning the tritium off the wall. We want to go back to deuterium experiments as fast as possible for what will be the final JET experimental campaign. So this will also be an exciting campaign because we're going to push JET's operational boundaries to maximize the scientific output.
Welcome back to the control room at JET, where we're celebrating 40 years of amazing fusion and plasma science here. The team over in the far corner, they've gone a bit quiet now. I think the last shot has just been run. They're not quite sure when the next one's going to come. Anyway, we have got a viewer in Estonia who I think has been reading my mind. He asks, or she, what are the main follow-up projects or initiatives in the field of fusion research that scientists are currently focusing on to carry forward and advance the research towards successful outcomes? Well, actually, I do have with me two people who are worrying exactly about that. Sun-Chi Chen, who's development engineer on STEP. We'll find out what STEP is in just a second. And Heather Lutus, who's the head of innovation. Whoops, ought to say that correct. Yep. At the UK AEA, the people who run this whole operation. I'm going to come to you first of all, Sun-Chi. STEP is the next step in UK fusion research, but it stands for something.
It stands for the Spherical Tokamak for Energy Production. So as it stands, it's the UK's flagship fusion programme to bring commercially viable fusion to Britain. So not only commercially viable, but sustainable, safe and secure energy. So it's a programme that's come out of the UK AEA. Going into next year, it will be its own company, delivered by UKIFS. So there's a lot of acronyms that we have here. UKIFS is the UK Industrial Fusion Solutions.
Yeah. So the T in STEP, tokamak. So it's basically the same kind of machine. It's a circular donut with a hot plasma inside it that JET is. So it's building on JET's science because it's taking the same approach. Yeah.
So it's taking a very similar approach to JET. I think the main difference, besides from sheer size between STEP and JET, is the shape. So it's still a tokamak, it's still a toroidal shape, but it's slightly more compact, slightly more spherical, hence the name.
I think of it as plump.
Yeah, plump. Some people like to call it a cored apple. So yeah, that's the main differences. But overall, in terms of fusion energy, we take many lessons from JET into STEP.
It's going to be bigger.
Much bigger.
Much bigger. And for energy production, so the idea is this is going to be actually trying to do what JET hasn't particularly been doing, which is going for producing more energy than it takes in.
Yeah, so we really hope to produce a net amount of power. So by doing this, we're incorporating a tokamak, a fusion device, into an actual power plant to put energy onto the grid.
So I'm going to come back to you in a moment, what lessons you've been getting from JET, or maybe from other machines around the world. Heather, innovation. So I gather that this means it's not just about fusion features, but actually the engineering here has been so spectacular, there are things to take away.
Exactly. So all the challenges that we need to overcome in order to create commercialized fusion energy, and all the challenges that they've already overcome in JET behind us to make such a successful experiment, you know, these are fantastic leaps of creativity, fantastic engineering. And what we're looking at is how you can apply that into other sectors. How can we help the space sector with remote operations? How can we help the hydrogen economy, because our fuel is a hydrogen isotope? So trying to think about things differently and also learn lessons from them, right? If people have solved things in other industries, let's bring it in. Fusion's hard enough, let's learn the lessons.
I mean, one of the really often shown piece of technology you have here at JET is this amazing robotic arm which sort of snakes its way around inside the huge
mascot, yes.
Undoes screws and all that kind of thing. So robotics, I think, is
Absolutely key, yes. Mascot's amazing. You know, it changed the inside of Jet, changed all the tiles, all done with remote handling. It was absolutely fantastic. And there's huge amounts that other industries could benefit from this. So thinking about the space industry, so if you need to remotely maintain a satellite, if you want to capture space debris, all those sorts of things, you could learn the lessons because...
I mean, Mascot works remote. You have your hands here and they operate the hands.
Haptic feedback, yes, you can feel what's happening. I'm told, I've never done it, that actually you could feel like a piece of sellotape on a surface. It's that sensitive.
I think you should go and demand a play.
I know, I shouldn't I? Yeah.
And then there's, I don't know, material sciences, the materials that have been made here.
Yeah, absolutely. So the materials that we needed to develop in order to make sure that they can survive the temperatures and things that you'll find inside a tokamak, they could be used for other sectors as well, maybe in the fishing industry, maybe again in space. For example, one of the manufacturing techniques that had to be developed for the windows that you monitor the plasma for Jet, the same group that made that made part of one of the instruments that was on the lander from Rosetta, so on Philae that landed on the comet. One of the instruments was going to look at the composition of the comet, and the techniques developed for the Jet windows were used on the comet lander.
Because, I mean, Jet, you've got temperatures for 100 million degrees. On a comet, below zero.
Yeah, and one of the really interesting things is you've got, you know, obviously really hot plasma, but then you've got really cold systems around your magnets. So having to deal with all those temperature differences means there's a wide range of other sectors where our technology is applicable.
Essentially, this is a challenge you're taking to STEP. I mean, where do you start?
Well, we start with the lessons that we learned from Jet. So both being tokamaks, there's so much technology that comes directly from a tokamak like Jet into STEP. Some of the challenges that Jet has faced, sort of solved by robotic maintenance, solved by new materials, solved by new technologies, directly informs the design of STEP. So a device like Jet is invaluable to us. I think coming into the end of...
It's going to be different. Like, I think Jet has got normal magnets. I think STEP will be using superconducting ones.
Magnets.
So you're looking at materials and stuff for that.
So I think a lot of the lessons learned in the DT campaign as well, the deuterium tritium campaign, these are the fuels that we'll be using in STEP as well. So plasma control is at the heart of this, and learning how to everything that goes into creating these conditions, everything that comes out of it, everything that we can measure, also informs the design of STEP. So everything is continually rolling, and then when it comes to the end of life, there are many lessons to be learned there.
Well, I was going to ask about end of life,
Yeah.
because there's going to be a big decommissioning program here, which we're going to talk about in the next segment. But presumably, you're looking at STEP and thinking, actually, there are some issues we could avoid.
I'd rather see them as opportunities to overcome. So we know that the magnets was a limiting factor on Jet, but Jet was never designed to create net power anyway. There's also the whole fuel cycle, so being able to generate the tritium that we need is a whole other research, sort of area of research for tritium breeding. And then the fuel cycle to be able to inject that back into the tokamak and sort of create a cycle that is self-sustaining.
John asks here, now we've had this letter before, what value of Q is planned for STEP? Maybe I can put it another way. How good is STEP going to be in terms of putting out power? Or are the team still working on that?
I think it's still something to be decided. It will be orders of magnitude larger than we've ever seen before, easily. And that's what will be necessary to sort of overcome all of the other potential losses to actually put net power onto the grid.
That's the challenge right now. The experiment works, they've proven it. Now it's all the things about commercializing it, making those efficiencies, and which is where, you know, there's a huge supply chain and everyone can get involved because it's all making that efficiencies, and in every part is going to help with that Q value.
And, I mean, is there there's a tension, I suspect, between the ambition to make it as big and or let's just control ourselves and make sure it works. I don't know if that's...
It is a trade-off. It's definitely a trade-off. It's a very ambitious program, but we have ambitious goals. So we have no problem with ambition, but it is, first and foremost, something that has to work, definitely. There's definitely, a trade-off and decisions that have to be made where we make ambitious decisions. With technologies that we don't know much about yet. So we're sort of developing these, and the lessons from JET, of course, make this easier.
That gives you confidence, right? They've had to fix things, they've had to do things differently. It's all the experience from JET that gives you confidence that this is something that's going to work.
STEP's going to be another part of the country, but you're going to keep working here. Your job's not done here.
No. I mean, the job in fusion is spread all the way around the country. So we've got a site up near Sheffield. There's going to be the STEP
in West Burton.
Exactly. But obviously we work with universities all the way around the country, and companies all the way around the country as well. So we do a lot of travelling around and gaining ideas and from different people.
Fantastic. Heather, Sun Chi, thank you so much for joining us. We'll be back with more in a moment.
RAISE stands for Remote Application in Challenging Environment. It's a robotic department within UK Atomic Energy Authority, and here we develop and do research on digital tools and robotics mainly to progress on the fusion energy. So haptics refer to the sense of touch, whatever we feel with our hands. In robotics, it's mainly used for bilateral telerobotic systems where there are two robots. The remote one is controlled with the local devices by a human operator. And this kind of system not only enable operator to control the remote robots, but also enable operator to feel the haptic feeling, what's happening in the remote side.
We have software and hardware platforms which allow people to quickly create very realistic digital touch experiences. A haptic training simulator, or more specifically a training simulator which has haptic feedback, is really what it sounds like. Basically, what we need to do when we have a situation where we need to upskill someone and provide someone with the opportunity to practice and rehearse, we have to give them a really high fidelity, realistic experience. It doesn't matter whether that is in dentistry or surgery. The key element is that the training experience should be as close to the real experience as possible. If you don't have the force feedback and that element of touch when you're rehearsing, you're not going to be well prepared for the real world and the real setting.
Long Ops is three stakeholders such as RAISE, Sellafield, TEPCO cooperative project in order to develop the next generation digital mock-up, as we call NGDMU. Currently, we at TEPCO are not familiar with this technology. We have to train operational skills in order to proceed with decommissioning tasks as safely as possible. We at TEPCO would like to apply this technology to actual work of fuel debris retrieval of Fukushima Daiichi nuclear power plant.
It's easy and efficient to develop digital mock-ups. Anything we can do with the digital mock-ups will enable us to deliver faster, safer and efficient fusion energy in the future.
Hi, my name is Varun Kumar and I work at the robotics facility in UKAEA. My day-to-day role involves in building software and hardware solutions for a fusion environment. Being in fusion, a new and developing area, always keeps me interested and keeps me motivated to be part of the organization. The robotics facility has a wide range of robotics that you can work with. Each part of robotics has its own challenges. It's something that very interesting to work with. The place where I grew up in India, so it was like an electronics market, I would say. So it was always buzzing and there was always people involved. There was always instruments or electronics lying around my house, and my day-to-day hobby was trying to break them apart, see how they work. So that curiosity sort of sparked when I was very little. I came to know about the robotics facility through the careers fair in my university. So the grad scheme provides everyone with an opportunity for self-development and an opportunity to work with people from different backgrounds and also deliver proper solutions in a very engineered way. During my grad scheme, I took part in various outreach and science festivals. The fascinating bit is that you get to explain fusion to a 6-year-old kid and fusion to a 60-year-old person who comes there. So that's really the fun part of being part of outreach. If you're planning to join the grad scheme, I would say keep an open mind and always keep learning.
welcome back to the control room at JET, where we are celebrating 40 years of amazing science being done at the Fusion Research Plasma Physics stuff here, and what's going to happen next. And in fact, so I am joined by Tim Bestwick. You are the Director of Strategy, Comms and Business Developments. That's just about everything for the future. Thank you. Laura Thorne, you're the Head of Portfolio Management for this is JDR, JET
Decommissioning and Repurposing.
Right, and I'm going to come to you in just a second. And Fulvio Thorne, you're also involved. You're the director of the Tokamak Science and Mast Upgrade.
Yes.
That's the continuing experiments here at CERN.
Yes.
In particular. So we're going to come to that. Now, again, we've got some people looking ahead here on YouTube. A question from John Carr. The decommissioning question is important. How much of the object is radioactive? How long will it take? Now, okay, I was going to talk about this anyway. So JET's been operating for 40 years. It's been running tritium and deuterium reactions, which produce lots of neutrons. They've made the inside radioactive, blah, blah, blah.
Yeah.
How are you going to deal with it next?
Well, the important thing to remember about JET is the tritium fuel, which has fueled the experiments recently. And that's actually the main source of the radioactive material that we'll be dealing with during decommissioning. So tritium, as we know, is an isotope of hydrogen, and it does embed itself in things that it touches. And that's the really tricky bit for decommissioning JET. And that's the thing which creates most of the what we call intermediate level waste, which is the inside of the tokamak. So if you've seen a picture of the tokamak, it's those tiles on the inside which form most of the intermediate level waste we'll be dealing with.
These will just be tiny, tiny layers, but enough to be something you need to deal with, worry about.
Yes, absolutely. So to deal with that tritium, one of the really pioneering pieces that we want to do in decommissioning is to learn how to get that tritium out. How do we get rid of that contamination so that we can leave behind clean materials, so that fusion really is a clean source of energy? So the way that we're going to do that is to heat it up so that the tritium will off gas, as we call it. It will turn into a gas, come out of those materials. We can capture that in water, and then we can remove it safely from the water and even use that tritium as fuel in new experiments.
And I mean, Tim, this may be for you as well. People have been really stressing to me, JET is not over, it's entering a new chapter, because actually there's so much science and engineering still to be done, because this is the first time people in your field have had to deal with this kind of an issue.
Yeah, so fusion is now in an era where lots of companies are looking to develop commercial product, and as they look to develop power plant products, it will be important to them to make the case that those can be safely decommissioned. So we're very conscious of the fact that JET is an example of having to do that well and properly, and as Laura was explaining, we're determined to do a thorough, good job to show that you can take a machine that's been running tritium for 40 years in the case of JET and decommission it safely and effectively.
I mean, it's a science project in its own right. I mean, it's not been done before. You're going to be learning, you're going to be recording everything you do all the way.
Lots of new information. An important aspect of it is how you capture that information and make it available so we can share it in the future. Yeah, absolutely.
I mean, the timescale, Laura?
So we aim to finish in 2040 to decommission JET. Yes.
Now there are going to be people who say, "Oh, that's it's such a long time. That shows how horrible it all is." But I don't think you'll see it that way.
No, I mean, relatively that's quick compared to fission decommissioning. Many of our fission reactors are in care and maintenance, and the half-life of tritium, which is the time it takes it to decay to half its radioactivity, is approximately 12.5 years. And that's much, much shorter than in fission, where the fuel will take hundreds of thousands of years to reach any form of meaningful decay.
There's another side to this. I don't know if this is right. These materials have been subjected to all kinds of extraordinary conditions, which future reactors will be as well.
Yes.
You're not just going to bin them, are you? I mean, I presume they're going to be taken off for all kinds of analyses, X-ray facilities and microscopes.
Yes. So the first thing we're going to do for decommissioning is retrieve some samples of those tiles that I was describing earlier, and we're going to cut them up, and various people are going to analyse them in different ways to see how they have been affected by the fusion reaction and how much tritium is in there, and therefore that can fuel our thoughts on really what materials we're going to use in future fusion reactors. What can we learn about what is the optimal material to line a fusion reactor with? How does it react with tritium? How has it reacted with the neutrons and the heat? And these are all things that we really need to study. And
it's a point that's often made to me that fusion, a lot of the research in fusion is actually in materials science, because
yes.
you need the materials which can withstand the conditions, which will be easy to use afterwards, keep the costs down.
Absolutely, and we'll be looking at that really closely as part of our decommissioning programme. And also we want to reuse a lot of the materials wherever possible. An awful lot of the materials from JET, we're focusing in on that radioactive element, but actually there's an awful lot of the plant which is never seen tritium and isn't radioactive, and things like copper can be recycled just like it would be in any other non-radioactive decommissioning programme.
I expect there's some rather nice alloys in there somewhere right now.
Yes, there's all kinds of materials which we can do very useful things with. And large areas of the plant, some of the diagnostics that we've used over the years will even be used on different experiments. We'll pick them up and move them somewhere else and reuse them.
Well, hopefully some of them won't have to move too far. So, Fulvio, you're involved in a project which is still continuing here on the Culham campus, which is MAST upgrade. Now, we heard in the last session about spherical tokamaks.
Yes.
So this is a squashed jet in a sense.
Yes, if you want, MAST upgrade has a slightly different architecture with respect to JET and most of the fusion devices that we have in the world. You can imagine the plasma, which is the fuel for the machine, to have a shape of an apple without its core, rather than looking like a donut. It's just a geometrical difference, but it is a substantial and important difference from the physics point of view, because it provides a different stability for the plasma, and we can use the plasma in a more efficient way. Of course, it is not without drawbacks, but we need to understand how the physics works, and that's why we have machines like MAST.
I mean, it's not a step back, it's a sort of a rethink, is it, of this whole tokamak torus design?
Yes, it's a slightly different architecture. You can imagine this if you want to have a comparison between the fusion world and the aerospace world, helicopters and airplanes.
And how far in are you with those experiments so far?
Well, we have just about to finish the third scientific campaign. We are doing experiments, typically for 6 months, and then for 6 months we go into an engineering break where we maintain the machine, we change it, we improve it. So this is the third time that we're doing it. The machine has started in 2020, and we've already reached very interesting results and demonstrated that the machine can work with a system that handles the power of the plasma towards the walls of the machine in a very efficient way.
We were talking in the very first segment about the exhaust gases which have to be managed, and I believe that's one of the big issues that you're studying.
Yes, if you want, fusion needs to address a number of challenges. And if you want, it's pretty much like drinking a cup of tea. You want to keep your tea hot, and that is what we call confinement. The plasma needs to maintain a certain temperature efficiently, but you also want to avoid burning your hand while you're holding the cup. And that is the problem of exhaust. And this is what MAST upgrade tries to address. Different tokamaks, different machines are actually designed to address different problems. We are still in an experimental phase at the moment, but we are moving quickly towards power plants. And we need to address all these problems, and MAST upgrade is excellent for exhaust.
And I guess that's going to be feeding out to other companies. Now, is it other companies around here who are doing, that you're dealing with?
We're working with fusion companies around the world.
Around the world?
Numerically, most of them are in the US. There are quite a lot in Europe, and there are others as well.
I mean, how does that operate? What do you do?
Well, we've sort of reinvented ourselves in recent years, and we have a series of centres of expertise in the different aspects of fusion technology. Because fusion isn't just one technical issue, it's a whole set of them. And we have centres that have, by virtue of JET and other experiments and MAST, really world-leading expertise in those areas, and we're looking to collaborate and share that with all the other people in the global community developing fusion.
I mean, are you encouraged by the number of private companies investing in this?
I am, because that's a demonstration of enthusiasm. I am not sure that all of the 40-something that exists at the moment will make it through to selling fusion power plant. That doesn't seem likely, but I'm certainly encouraged by the level of passion and enthusiasm in the sector. Absolutely.
I mean, it's like engineers buying lottery tickets, isn't it? Someone's going to win, maybe.
I'd like to think it was a bit more planned than lottery tickets. But the bit I do agree with the analogy is the prize is enormous.
Laura, another question has come in, again to do with the decommissioning. When do you actually start doing that? And I want to know, because I want to come back. I want to see some of this happening.
So it's going to be 2026 when we actually start robotically dismantling the Taurus. So we're going to use robots, we're going to put robotic arms in there, and we're going to use the robots to unscrew tile by tile and take out that tritiated material, those tiles that line the jet. And we will be then performing analysis on those, but more importantly, we will be detritiating them and cooking the tritium out of them.
And until then? Is it all planning, or are there other things that you can do?
We've got the samples that we're going to take out.
Oh, so you're doing those first?
So I've got to do those first. That's going to be next year, and that will be a short campaign using the robots. And in the background, we are going to be doing a lot of planning, because we've got to really carefully plan. We want to do it safely, obviously. We've got to be really careful that we're as safe as we possibly can and as well planned. But we can also take apart lots of the outside pieces of jet. So there's many supporting buildings. There's lots of porter cabins and ancillary plant that we can start to take out of the buildings and actually start to turn those buildings into something new and interesting that can help advanced fusion.
Well, I was going to ask, I don't know if it's Tim, if it's your business. I mean, when jet is removed, there's going to be this huge hall that it was in, purpose-built to be incredibly secure and so on. You're going to put something else in there?
Yeah, exactly. The J1 building that jet's in is, as you say, a great big hall with cranes and infrastructure and shielding and all those support facilities. And one day, jet will be safely out of it and taken away and decommissioned, as Laura described. You won't be surprised to know that quite a number of organisations have already contacted us and said, that building you've got that's coming along line, any chance we could make use of it? So that's certainly something that's under active discussion.
Have you got any use for it, Fulvio? Go on.
Well, let's
put
hope.
a nice big one in there.
We definitely we will definitely need to continue researching the plasma, if nothing else, because all the technological enterprises that we've always had required research and required innovation. So most definitely it would be quite exciting to see how we're going to use J1.
I mean, MAST, I think, is in one of the original Cullen buildings from the 1960s.
It is.
These things can have a long life. I mean, there is a question come in from YouTube. What else in way of tokamak or fusion research is going to be continuing here at Cullen in the future? I mean, you're...
Yes. Well, of course, we will continue doing plasma experiments because we want to tame the plasma and teach it a few new tricks. But we will also develop diagnostics to understand better how the plasma behaves. We will maintain the capability of operating these machines, which is very complex. It's a little bit like piloting a Formula One car. And we will have a thriving program of theory modeling. We also need to study in silico, in numerical simulations, how the machines are going to behave in the future, especially the power plants.
So you're going to be busy.
Yes.
Fulvio, Laura, Tim, thank you very much. Do stay with us and join us after this.
The UK Atomic Energy Authority intend to put fusion energy onto the grid by the 2040s. To do that will require a leap from the theory and science of fusion into the manufacture and delivery of fusion machines. The Fusion Technology Facility, or FTF, in the heart of Rotherham's Advanced Manufacturing Park will be at the forefront of that transition. Fusion promises to be a safe, low-carbon and sustainable part of the world's future energy supply. It's even described as the ultimate energy source, and it's based on the same processes that power the sun and stars. When a mix of two forms of hydrogen, deuterium and tritium, are heated to form a plasma at extreme temperatures, they fuse together to create helium and release a huge amount of energy, which can be converted into clean electricity. Our teams at the FTF specialise in a wide range of disciplines that are required to make fusion energy a reality. Some of these include manufacturing techniques and equipment qualification. They develop and mature manufacturing technologies of critical components and develop inspection technologies for controlled testing of components under the extreme conditions that are found in commercial fusion. Digital image correlation. They use an advanced diagnostic technique with digital cameras and computer vision technology. It allows them to see the deformation of a component under load in real time and provides accurate data that can be used to validate simulations. Thermal Hydraulics, who use experiments and modelling to develop an understanding of component cooling and heat transfer for fusion. This includes research into novel cooling fluids and high-pressure pipework, from the small component scale through to the large plant scale. And Chimera, a one-of-a-kind materials testing facility. It uses high temperatures, high magnetic flux, and a large vacuum chamber to replicate fusion conditions. This means that materials can be rigorously tested and qualified before being introduced into the fusion energy plants of the future. Achieving fusion involves working at the forefront of science, engineering, and technology. The Advanced Manufacturing Park was chosen as the site for FTF for its geographical location, its proximity to world-leading manufacturing resources, and its proud industrial heritage. With our pioneering research, alongside links to local universities and industrial partners, UKAEA's Fusion Technology Facility puts South Yorkshire at the centre of a growing, sustainable energy economy.
My name's Diane Ashmore and I work for RACE, which is the robotics department of the UK Atomic Energy Authority. I look after all of the admin for the RACE department, so day to day it just means supporting the whole team with any admin inquiries they have, so booking travel, organising new starters, meetings, everything admin related. I came to work at RACE in 2014 after it had just been created, and I just love it. It's very interesting. I get up every morning and I really enjoy coming to work. It's a real challenge. No 2 days are the same, and yeah, I just really love it. My dad had always worked for the AERE, as it was then, and had an interest in electronics and electrical things, so I just thought that sounded like a really cool place to work. Working within the fusion sector, it's so beneficial for the future of the planet and everyone. I just wanted to be a small part of that. So what I would say to anybody that is thinking of applying for a role with the UKAEA that hasn't come from a background in science and technology is just apply, because you don't need to have that background, and I'm proof of that.
Welcome back for the final session here from the control room at JET. We're celebrating 40 years so far of the science done here, and we've been looking forward to what's going to happen next. Actually, what's going to happen next, I just heard the countdown for another plasma shot going on in the corner. There's a kind of quiet intensity as it all happens. I've been watching a few of these. I'm joined for this final session by Joe Mills. Now, you're Executive Director for Engineering and Computing, so that's quite a big job title.
Yep,
okay. David Keeling. I feel that you want to be over there, don't you, at the moment?
Yes, very much so. One of the best parts of my job is being one of the session leader team. So one of the people who gets to sit there, press the buttons, and trigger these countdowns.
See, and so you're quite. How many of these have you heard in your time?
Oh, it's difficult. I did my final shift on JET just last Tuesday.
Right.
So I looked back on the system, because it's all recorded, and I found I've done 194 session leader shifts, so just shy of the 200. But multiply that by 6 or 7 pulses per shift average, because of course some didn't get any, and that's a huge number of pulses, but every one of them great fun to work on.
I mean, I heard that you passed a record of 100,000 shots a couple of years ago. Is that right?
Yes, that's correct. So the pulse numbers read out by the automatic system at the beginning every time we trigger. This is on 105,700 and something. Yes, so we went past the 100,000. JET was designed for many fewer shots than that, I believe. But,
well, maybe.
We
also have here Alan Kay, who was the chief engineer here.
Yes, I was chief engineer here back at the time, and at the end of the JET joint undertaking, and in the first few years of the operating contract with UKAEA.
This is when, right?
A very interesting time, because I took over from Enzo Bertolini, who retired in the late 90s, shortly before the QTE-1. So I was actually in the chair, although not called chief engineer at that time, for the DTE1 campaign.
So that was
a very exciting period. Yes.
So
yes.
take us back. You joined when?
I joined JET in 1983.
So you were here, as it were, almost at day one?
I joined a week after first plasma. The project started, the construction started, I think, in 78. The team arrived here in 73, which is also when I arrived, but not on JET. Yeah. But that period up to DTE1, that was a memorable time. I thoroughly enjoyed that.
But I imagine, I was reading the reports from the very beginning of JET, the first annual report, and there was this sort of sense of pride that the very first shot worked. I mean, what was the team like then? I'm interested in the people you were working with.
Yes, I remind you, the first shot actually was a week before I arrived.
Yeah.
So there were people who had a better recollection than I. But we had a splendid team at that time, undoubtedly. I mean, the real attraction to a person who's interested in fusion physics and engineering, you know, you've got this machine, which is the biggest machine in the world, generously funded, with a couple of hundred professional scientists and engineers at the cutting edge of technology. A very exciting place to work. So the fact that it worked first off, I mean, the credit for that must go to the director, or the chief engineer, Paul-Henri Riboud, of course, who had tight control over what was going on, and excellent engineer.
I mean, the other thing is that this was, you know, I suppose they'd done this at CERN, but this was pretty unique in the idea that you had people from every country, basically, in Europe coming to work together.
Yes, we did indeed. I mean, I joined as a group leader in the radio frequency division. We had a German director, a French chief engineer, a French division head. I had working for me French engineers, German engineers, an Irishman, as well as half a dozen English people. It was a fascinating environment to work in. The interaction between all of these peoples and the different cultures they'd grown up in made the job fascinating. It didn't necessarily ease it, but I think it was a real benefit to the project.
Yeah. David, I'm quite interested. I've read certain. I mean, we talked an awful lot here about the engineering and all the components that have to be brought together, the magnets and to make it work. But you've been team leader in there, and I keep on hearing that it's actually, as it were, not the engineering of the people, but the meshing of the people.
That's right. Yes. So there's a huge number of people here. Well, you can see behind us there's people whizzing around all over the place. They all have their very particular jobs within the control room, but not just here doing the shift. It's also the preparation beforehand as well. So the experiment that will be happening now would have been in preparation for months, possibly even years beforehand, with the scientists who have the original idea of the experiment communicating very closely with all of the control room team that they need to run the machine for them when they get here. So this just wouldn't work if people didn't work well together. So that there have to be lots of respect in meetings. There has to be a free flow of information and ideas, and everyone has to be receptive to everyone else's idea, because each person is an expert in their own part of it, and they've got to know that they can trust the experts from every other part of the operations.
I mean, this planning would be sort of exactly how much current you want to go through the plasma, the density of the plasma, the magnetic field configurations, that's all programmed in.
Absolutely.
And also diagnostics, you want to be looking at it in exactly the right way.
Quite, yes. I mean, there's thousands of parameters we can adjust on this machine. It was a research machine. It was designed to be as flexible as possible to get as many results out as we can. There's thousands of different ways of measuring that plasma as well. And this all has to be set up exactly in detail to get the exact physics that you want out of it to further the knowledge. There's no point in doing the same thing again that you've always done, which again is why it's quite so difficult in here, because we're always pushing the machine to its absolute boundaries. We don't do the same thing time after time. It's not interesting. So we're always trying to go that little step further.
Joe, you were nodding all the way through that.
Yeah, that all sounds very familiar. I mean, I suppose I've had two careers on JET. I started out on JET as a graduate, as an engineer, and then I had the privilege of leading the ops team through DTE2. But I mean, just listening to David and Alan talk about the teamwork, I just remember early on in my career here, there was a few sort of catastrophes, and I was panicking, thinking, oh God, how are we going to solve this? And it was so clear immediately that the sole focus of everyone, in fact, everyone got much more engaged. Oh, brilliant, something's broken, let's have a go, let's try and fix it. And the idea of having these teams around you that were not looking to appoint blame, just looking to figure out how to solve this so we can get the machine sorted again so that these guys can take over and start operating it again. It's absolutely key to this place.
I mean, when I was talking to Tony Donnet, he made this point that, and this relates to moving the operations to ITER in a sense, that it takes 2 or 3 years for everyone to really gel and understand each other. It's not just getting those nuts and bolts, but there are those sort of human lessons that have to be relearned or transferred, I guess, because it's going to be an even bigger challenge, I suspect, at ITER.
Yeah, I mean, the knowledge that's been accumulated in this team is unique and incredibly valuable. So we're spending a lot of time figuring out how can we pass that on so that ITER don't have to go through that whole cycle, because it does take years, if not decades, to accumulate the kind of knowledge that these chaps have in their heads. So yeah, we want to give ITER and other machines a flying start. So we're thinking about how do we get that knowledge out of their heads, and how do we sort of teach that culture, that openness, that team working to the next generation of machine builders and machine operators. So that's a big focus for us at the moment.
You talking? Yeah, go on.
No, I was just going to add on to what Joe was saying, because we had at the end of the joint undertaking, we lost 150 European engineers and technicians, particularly difficult on the engineering side. And you noticed that. You went from a scheme where something went wrong, you called in the people who probably designed it, but certainly knew all about it, and solved the problem. But in the first few years under the operating contract, of course, you'd lost a lot of this capability. And it's taken, certainly the period that I was still here, to rebuild that capability to the level that existed previously. The cumulative experience is a very important issue.
You're talking about building up to the deuterium tritium campaigns, which I guess for an outsider just sounds like a change of fuel, but it's a big deal.
Yes, it was a big deal. So I think particularly of the DTE-1, when I was here, of course. I had an interesting interaction with Martin Karlhager, who was director at the time, because the proposal was to use the field coils at 4 Tesla. They've been designed for 3.2 Tesla. But the fusion yield increases strongly with magnetic field. But there was an issue of whether the coils would actually survive this for the duration of the
I hate to
campaign.
say this, when I saw that you were the chief engineer, I was wondering if there was some moment at which you said, the tokamak cannot take it, Captain.
Well, Martin said to me one day, he said he spent his entire research budget for 5 years on achieving 4 Tesla. And I was going to tell him he couldn't run it. So at that stage I invented the equivalent pulse, which is still in use today, which essentially assesses the cost of a 4 Tesla pulse in terms of the number of equivalent pulses at 3.2 Tesla. And there's perhaps, one pulse at 4 is perhaps 1,000 pulses. But somebody has to take a judgment. Is the physics results you get from this pulse justified the consumption of fatigue life that it produces?
So it's a wear and tear issue, that you age the thing just by pumping so much current through the magnets.
Right, and of course it's only the people in detail in the physics who can take that judgment. What do you actually learn from doing this pulse that you don't do at 3.2 Tesla?
I mean, these are the details we never ask about as journalists, you see. It's actually quite interesting when you talk to people at leisure about what it, those kinds of issues. I mean, David, I don't know if have you ever said it cannot take it? Or
Well, in a way, yes, because the equivalent pulse that Alan's just been talking about, we use that in the program execution committee that approves the experiments to be done. So one of the experiments we will hopefully be doing later is working up at 3.86 Tesla, so really close to that 4 Tesla limit. And of course, it will consume an amount of the fatigue lifetime. So we ask for 0.2 equivalent pulses of the 100 that it can take. And that has to go through committee. We have to sit there in committee and judge whether the science that that's going to give us is worth spending 0.2 equivalent pulses on.
Yeah.
In this case, yes. So we will be doing that experiment, but it's a lot of judgment in it.
Alan.
I would make one other point on the DTE1 campaign. I was in the chair as engineer in charge for the first pulse of DTE1. And I recall everybody reported to me and it all looked to be ready. And my finger was on the button. I thought, are we really ready for this? And I thought, yeah, I have confidence in this team. So I pressed them up and it went through very nicely.
And we're all very glad you did.
Are you going to be sitting in that chair next week? You're going to come back and reclaim and say, we're going to really push it for the last shot?
No, at this point I have to confess that I leave it to the experts. I try and just deal with the money and resources to keep out of their way so they can do the tough stuff in the control room.
But it must be an interesting issue. You're coming up to the last week of operations here.
Yeah.
You know, you want to...
Oh, I'd like to be around. I mean, I try and sneak in all the time, but a colleague, Fernanda Rimini, who's one of our top scientists, she's convinced I'm a jinx. So if she sees me in the control room and there's a big pulse, she banishes me.
Right.
And it has about a 50% success rate. Occasionally that will help make the pulse go through, but it's not 100% infallible. So I try and get in whenever I can. It's a brilliant place to be when they're operating. It's so much fun.
Fantastic.
David, are you going to come back?
Yeah, well, you talk about pushing it to its limits at the end. Of course, as I've said earlier, we try to push it past its limits all the time.
Yeah.
But we did think, what special things could we do right at the end there? And there was actually an experiment the other day looking at the runaway electron beams, where you get really energetic beams of electrons going around, which can cause some serious damage. They're a worry for ITER. We've done a lot of research on them. So we did a special one of those where we blew a chunk off the inner wall.
Oh, right.
Essentially, we knew it was going to happen, so this is the time to do it, so we did it on purpose.
I mean, what's the legacy? I mean, it's 40 years it's been running, this place. To me, it seems extraordinary, but, you know, in a few words from each of you. Alan.
So you're right, the 40 years is very impressive. I joined in #83 expecting the project to end in 1990. Here we are 33 years later, it is actually ending. I think the key legacy that I see of JET is keeping the whole field alive and vibrant through what were very challenging periods over that 40 years, where enthusiasm for spending a lot of money on something as challenging as thermonuclear fusion definitely waned. And the JET being locked into Euratom with many countries participating in the council, very difficult to stop. And I think its main contribution is keeping the field alive and vibrant over that 40-year period to a situation now where it's as vibrant as I've known it in all of the time that I've been working in the subject.
David?
Yes, well, coming straight along from that is just the sheer number of people that have trained as scientists, trained as engineers on this machine and on this site. This feeds the entire industry, the fusion industry and wider industry as well. It's not everyone stays in fusion, but I think we've got apprentices here, ex-apprentices certainly, who would say that this was the most fantastic start that they could have thought of, and that feeds globally, I think.
Joe?
Doesn't leave much for me, but I think Alan and David have captured the key points. I mean, I suppose it's fair to say that there isn't a magnetic fusion device in the world that would be where it's at without the results that have come out of JET. So I mean, really, it just underpins the whole field. So that's a huge part of its legacy as well. It's not the only machine, but it's certainly been one of the most important, and that's exemplified by the fact it's been going for 40 years. We would not have done that if it wasn't producing all these great results, which have now fed into this vibrant ecosystem that Alan refers to. There are lots of new machines coming online, which is very exciting, and a lot of them owe their sort of a lot of their technical experience to JET. I think that's its legacy.
Joe, David, Alan, thank you so much. Thank you for tuning in to this YouTube special, talking from the JET control room, celebrating 40 years of amazing science, and remembering that there will be more to come up. I'm Roland Peace. Thank you very much for joining us. We're closing with some thoughts from many of the staff around the JET site. what they think of how it's all gone.
Put simply, JET is the most important fusion experiment there has ever been. It's the most important experiment that the world has ever done in fusion. And it has left an indelible mark on history. Actually, without JET, the fusion field would not be where it is. The fact that we got the record power in 1997, that gave us confidence to go ahead and build ITER. ITER wouldn't have happened without those experiments in JET. And the fact that we repeated that in 2021 and that the DT results matched our experiments gives us confidence that we're on track to get to high performance in ITER and to take the next step towards fusion power plants. These things just would not be happening without JET.
I arrived at JET in 1999 and I knew I was joining a fantastic team. It was actually intimidating at first, meeting people I've read the papers of, but the team was very welcoming, and I evolved here as a scientist, as a group leader, and eventually as a task force leader. And what I found in JET is indeed great teamwork, a lot of enthusiasm, resilience, and yeah, when I think about this, I feel very good about it.
Okay, in my opinion, there are two types of engineers. There's some who enjoy the speculative engineering of designing machines that are going to be built in 20 or 30 years' time, and maybe they'll have retired by then. Nobody ever really measures their success. But the whole of the JET team, including me, I would say we're the type of engineer who actually enjoy the cut and thrust of keeping a machine like this running. And when there's a problem, we have to work together to solve the problem. And you can tell whether we've got it right. As you can hear in the background, there's a countdown happening. At the moment, we've got it right. And I really enjoy working with a team that's able to do that.
And then whenever Eurofusion took over in 2014, it was really quite exciting time. So I tried to be 1 week a month at JET, which I certainly succeeded in the first years. And this was a very interesting time to see the vibrance, to see the excitement of the people, to really go in the control room and see people there and no, it's really great. It gave me the feeling this is what what fusion is about. You know, it's really great stuff happening there.
Europe, of course, is complicated and decisions are slow to be taken. But at the end, I think they are taken, and I think they would have been taken in the end. I think inevitable, almost inevitably. So it's difficult to imagine a European program without JET. But you know, the JET represents so much not only for Europe, but for the the world fusion program as a whole. JET has been the leading experiment for the last 40 years. Not only in Europe, but everywhere.
JET changed enormously. I mean, JET's been in operation for 40 years, right? You can see just looking at these pictures behind the difference in the internal configuration. The machine was substantially developed over that period, but it has to be said that the intrinsic design of the base machine and the fact that it allowed such development over such an extended time period is a tremendous testament to the original design.
I'm not sure I know the answer to that, to be honest. I mean, I do like working at JET. I think one of the main reasons, and I'm still staggered by this, that after 40 years of operating it, there's still things I don't know about how to operate it. So I learn how to do new things, and of course I also pass on what I know how to do to other people, and that makes it a very interesting job.
It's been a huge part of my career, and I've done so many exciting experiments on JET and had the great privilege to lead a couple of campaigns as a task force leader. JET has been a big part of my life, and I will be very sad to see operations end, and I will miss the late shifts, already do miss the late shifts, and the early starts because of the camaraderie of the team.